Good evening. Thanks for coming out to Lambda Nights. This is the first of probably dozens, this is a franchise of nights of Lambda. There's the day, which is the proper sort of, and then the respectful one, and then there's the night, which is the not so proper or beer-centric version. So, my name is Garrett Smith. I'm a programmer at CloudBeats, and I'm going to be talking about some kind of a weird topic. But I'm super excited about this topic. This is like one of those things where you know the phrase geeking out on something, where you love something but it's really weird, and you're a little afraid of people knowing that you love something so much. And this is one of those topics that I'm glad to be among people here who presumably are interested in functional programming. So I'm not ashamed to tell you these things, but I wouldn't get this excited about typical functional products. So this is about functional code considered beautiful. Oh, come on now. Sorry. I'm letting this on Microsoft. There we go. Okay. So, yeah, no one has reception down here. What? Oh, here? Okay. No one has reception down here anyway, so forget that. Usually I say if you're going to throw tomatoes, throw it at that in Twitter, so it's not fun. It's real time, but don't worry about it. So, before I get into this, I want to describe beauty, what the topic of beauty is related to functional code. So to do that, I want to sort of set this concept up. In functional programming, in programming in general, there's this idea of correctness. So you write some code, and people generally want it to be correct. And in certain circles, correctness has a really high value. You'll hear it all the time. Is this, how do you know this is correct? Is this correct code? And there are all sorts of ways to reason and prove, and it's a big centerpiece of software programming. I don't like this term at all. I don't like the term correctness. It implies that there's some sort of absolute standard. There's like a God, there's a programming God that says, whatever you're doing, here's the standard, good luck. You're either going to get it correct or incorrect. That's nonsense. Software is not, there is no standard of software. Software is a series of experiments. It's, we're trying to get computers to do things for us in some sort of social context. And just like in any social setting, we're going to get things wrong. We're going to guess at something. We're going to, our requirements are going to be so-called requirements. We're going to be wrong. We're going to solve the wrong problem correctly. So we've got something that does this thing, and then we look. It may be correct or not. Now, that term correctness is irrelevant. You take that thing and observe it, and then say, is it working the way we would like it to? Is it suitable? So standards of absolute truth bother me in general. They bother me quite a bit in software. I prefer to use this term, intent. So when we talk about software, rather than thinking of it in terms of, is this thing correct or not? Think of it in terms of, am I clearly expressing my intent? So it is to say, when I look at this code, is it clear what the intention of the author is? So that to me is something we can actually think about and we can talk about. And we can say, is this clear? And you can say yes or no. Is it correct? I have no idea if it's correct. It's really kind of a silly thing to talk about. So I like intent, and I'm associating intent and beauty here. So something that is clear, is unambiguous. You take a look at it and say, this makes sense to me. That's beautiful code. That's my definition for this presentation. You might say, beautiful code is something that complies with some coding guidelines. I say if it's really unclear code, if it makes no sense, that's ugly code. It doesn't matter how aesthetically beautiful it is. Syntax and semantics and the program structure has a lot to do with clarity. But really, at the end of the day, are you expressing yourself so that others can understand it? It doesn't matter what the syntax looks like. If the answer is yes, I say that's beautiful. If it's no, I say that is ugly. There's a range between beauty and ugly. So that's the backdrop here. So what I'm going to try to do is prove, maybe not prove, but hopefully persuade you that functional programming gives you a really good shot, helps give you some tools to create beautiful code. Are you as excited about that as I am? Yeah. Okay, seriously, it's really cool. You write software, so to be effective in communicating with other people through the software you write. Okay. So, clear intent. Here's a very simple function in Python. So I'm going to be using two languages in this presentation, Python and Erlang. This is in Python. How many people here know Python at all? Okay, here's the proof. 4 class. Okay. So I will, I'll explain this. I've used Python because it's very simple. The author, Rassam, created this to look like pseudocode. So that is the idea here. This is actually runnable. You can type this into the Erlang interpreter. You can run this, or the Python interpreter. You can run this. This is valid Python code, and it's fairly straightforward. But the def here is setting up a function definition. You have 2 arguments. They're named here. You've got an item, array. This little equals gives you a default. So if you don't specify this, you'll get this as a default value. And here we have array as an object with an append method. How many people are object-oriented folk? Java, C++. How many people are not programmers? Okay, so everyone's a programmer. Object-oriented camp. Everyone who's in OO, please raise your hand. Most of you should be, okay. I just know that. How many here would say functional, some functional derivative, including Lisps? Okay, more. Okay, so 1/3 to 2. So I'm probably preaching to the choir to some extent. So consider this then. If you're already persuaded of the merits of functional programming, consider this a way to possibly think about persuading others to try it. So it still will be valuable. Many of this will be like duh, yeah, okay, got it, all right. So there's going to be, this may be some sort of, may not actually be persuading because you're already persuaded, but maybe there's a model here that you can buy into and help to evangelize the process. I actually think this is valuable for the human race, so it's really important for having time. Okay, so what's happening here? This thing is called an init array. So what do we presume it's going to do? Initialize an array. So we pass in an item, and here is an optional argument called array. If we don't pass this in, it's going to get a default of an empty list. And what we're going to do is perform an operation, append on the array with the item, and we're going to turn the array. So naively looking at this, I would say this is pretty obvious. I'm happy as a reader of this saying, I understand the intention of the programmer, so therefore this thing is beautiful. That's my opinion. All right, so let's run this and see what happens. So I'm going to print init array. So that's a print statement in Python, and I'm calling the init array with the number 1. And as you would expect, I've got an array here, or a list in Python, with a single element of 1. Reasonable? Is everyone cool with this? No surprises. This is what one would expect. Now let's call it again. Right? I'm calling an init array with the same value, right? The same type of thing, but I'm getting this. I'm getting a list now that has 2 elements in it. Now, I'm a Python. I've used Python for many, many years, and the first time I saw that, I was very, very surprised. That is not expected to me. That is a surprise. So now my question is, I don't understand what this often means. But I think I understand. This might be a bug, or it may be intentional. I don't know. At this point, I'm confused. Let's try it one more time just to make sure. Yep, indeed, we've got a 3rd one here. So we can keep going this thing, and somehow we're mutating some kind of state, which is somehow global that we're not aware of. But here's what's actually going on. If you understand the way Python functions are constructed, it makes perfect sense. So here, let's describe some context that will help us understand this. So what's going on here in Python when this function is created? This array is an actual attribute of the function. So the function is essentially an object in Python, and it has these attributes. These are arguments, and some are optional, some are not. So you have metadata, or information about the function attached to the function, bound to the function when it's created. So this array is an actual attribute. And what we're doing here is we're modifying the attribute of the function. So we're sort of doing metaprogramming, probably by accident here. I'm going to guess this is not intended. But if it is, it's a strange function. But in any event, this is what's happening. I'm modifying an attribute of the function, so every time I call this, I have this what's called a side effect. Something is happening outside of the function. In this case, it's the global definition of this function itself. And every time I call an array, I'm modifying this attribute of the function. And of course, it makes sense of that. We're like, oh, of course, that's exactly what makes sense to me. All right, so this is this topic of context. What I'm going to do is go through different models of structuring an interface, a programming interface. I'm going to go with object-oriented, function-oriented. I'm going to move to a pure function, and then I'm going to surprise you with something else. And the intent here is to talk about this idea of context. So in the previous example, we saw this idea of clarity of intent is bound up in knowing what the heck is going on. So knowing what the heck is going on, I'm calling that context. So we're going to look at these different models and ask the question, what's going on? What's the context that I have to keep track of? All right, so let's take our favorite here, object-oriented. I think for a lot of people, you become uncomfortable when you see that term. You're just like, because I know you're functional programmers. But I gave this talk at the Norwegian Developers Conference, which is primarily .NET, and almost everybody there's a C# developer. So object-oriented is like, totally, I'm on board with object-oriented. So let's look at this. All right, big blast of Python code. This is a class definition in Python. It's the same syntax as before, so we're talking Python. And we're creating a class of type account. There is no superclass here. And we have these things, which are functions, but they're bound to the class, so they're a part of the class definition, so they're called methods. So the method is bound to an object. You create an instance of the class, you get an object. That object has functions attached to it. So it's this coupling of state and functionality, basic object-oriented premise. And these functions have this self-argument, which is a reference to the object. So when you call this thing, it gets implicitly will be passed a reference to the object itself, and then you can go to town on it. This is self is basically like this in Java or C++ or C#, but it's passed explicitly. There is no implicit self-reference. You can even rename it if you want. The convention is to call it self. Okay, so these are the functions, and what we're talking about is an account that can be initialized. That's a constructor. You can withdraw funds from it. You can deposit funds into it, and then you can retrieve the balance. So this is a type. You can think of it as a type, and it's got some functionality associated with it. So let's look at each one just so you understand what's going on here. This is code, so we want to understand the code. All right, so this is the class, and this is the init function. This is a convention in Python. You can blanch and cringe and hate Python. A lot of people do. They don't like this thing. But this is effectively a constructor. So when you create an instance of a class, that is, you create an object in Python, this gets called. And you pass in these arguments. So this argument gets passed in, and we're going to take initial deposit, and we're going to assign that to balance. That's how we create an instance of account. Cool? All right, let's move on to the next one. Withdraw. Same idea. We've got a function here, which is bound to the object, so we get a reference to self, and we're going to withdraw an amount. So we're taking money out of the account. So we apply a min function here to make sure that we're not taking out more than we have. So that's kind of the business logic. You'd say, oh yeah, the intent of the author here, the intention is to make sure that we're not taking out more than is in. So we're going to take the minimum of amount and balance. Then, next thing here, we're going to modify balance, as a function here of balance and allow. We're going to subtract allow from balance and assign the result to balance. And then finally, we return from that call what we actually took out, because it might not be what we asked for. Straightforward? Deposit is the opposite, we're adding. Even more straightforward. And then finally, we are going to query the balance and return balance, etc. Straightforward. Okay, here's how we use it. This is now creating an instance of the account. So I have an object reference here. I'm going to invoke the method on this. So this method, which we define as bound to the object, and I'm going to withdraw 50. And that's the amount withdrawn. I'm going to get the new balance using our function, or our method get balance. And I'm going to print the result. I withdrew pointer there, reference, still have reference, and then I pass in these arguments. So that's the way I print that. All right, so now the exercise here. So that's the setup. The exercise here is to think about context. Remember that original thing, we had this kind of confusing thing that we had to know about in order to reason about the code and to understand. The question here is, what do we have to understand about this function to understand what's going on? So looking at this thing, I see a self and amount. So I'm looking through this. And I'm reading this, and reading this, reading this, and then boom, I hit self balance. And as a reader of this, I'm curious what balance is. Where does it come from? How is it initialized? What is it? Right, so I have to then understand what that context is. This is effectively global state. Like global state, you initialize something, and then you reference it later. When you reference it, you probably want to know how it got there. How was it initialized? In an OO context, these things are called instance variables because they're bound to the instance. It's like global state, but it's within the object. You have the same problems with instance variables as you do with global state. You have to wonder where they came from. Who can modify them? Are they being modified at the same time? Like this. Right? Like this. So here's a case where self.balance is being modified by the withdraw and also by the deposit. So this is more context I need to worry about. What happens if this thing is being used at the same time? Right? There are things that you have to keep in mind. So you're keeping your eye on these things. So we're counting them. It's not the end of the world. We're just keeping track of them. If you happen to run these two things without control, without synchronization, you're going to foobar your account. You're probably going to be shut down today. Furthermore, this initialization of, and this is let's see if I can fix this. Right? The initialization of balance in the case of where you're inheriting from multiple, so this is inheritance. So, what's great about OO is you can inherit and you can get all sorts of power. With power comes great confusion. Here we have base account. Who knows what that is? It's a superclass. It's a mixin of some type. And we have auditable. I just made this stuff up. But you see this in OO all the time. So now we don't even see the word balance anywhere. And I have to go look in some other location. And this can actually balloon off into a tree of extremely complex interactions. So in OO, you have a lot of things that you can potentially have to deal with. How many people have debugged this sort of problem? Where you have mix-ins, which you balloon out into other things, and you have some initialization of state where you have no idea what's going on. That's context. So to understand what's happening with the withdraw function, you need to understand all of this stuff. Really, you do. And you can get the same sort of mysterious behavior as the first example, where you're doing print and then what? Yeah, it's magically horrifying. It's like a horror show. Like it's not entertaining. It's bad. So you go here and so anyway, this is OO. This is the world of OO. So the way we can fix this problem by getting rid of a class, and that's the next example. So we look at OO, and I've shown basically how state management can become very complex and implicit and context that you're not easily aware of. That undermines the meaning and intent of something. So I call this ugly code. It's not beautiful. It's not. It's terrible. Maybe the base class case here is okay. That's okay. I can understand that. But this stuff, that's terrible. And this is actually the way that most of the contemporary software is written. You use OO in order to have inheritance, in order to do this type of thing, in order to have all the power and magic, as someone said here, but you lose clarity and insight into the context. So let's fix that and move this thing into what I call functional oriented. This is a thing I think I made up. I don't think this actually exists as a term. But what we're doing is, we're going back to the days of C, when we didn't have OO. We didn't have like object dot, magic reference to some function. Everything was a function. So we can do that easily. We have sort of an object-oriented API. So this is the same idea, but there's no class. It's just 4 functions. And I'll go through each one. But we have the same basic API. So there's a new, whenever we initialize something, we're going to withdraw, we're going to deposit, we're going to get a balance. Same behavior, same business logic, different method, different approach, different sort of pattern. No objects, only functions. Okay, so let's take a look at new. So in this function-oriented, there's no object that's true. So we have to store a payload somewhere. So what I'm doing here, the payload being we have to manage our balance in some fashion. So what I'm doing is I'm using a dict, and this is a map structure in Python. And this is how you create it. So the curly brackets say, that delimits the dict, and then I've got a key and a value. It's a convenient way to ship state around in Python. I could have used a bunch of different things. I could have just used the value itself. I could have used a tuple, right? But I chose to use a dict here because it's convenient. All right, so now the withdraw function is taking, rather than self, which was bound implicitly, it takes a specific account. So now I'm passing, I used new to create the account, and to withdraw I have to pass the account in. Back in the days when we only had functions, this is how it worked. So I apply the same min function, I've got allowed, I subtract the balance, and this is how, in Python, this is how you reference an item in the dict. It's square brackets, and this is the key. So that's this is the value, this is the balance. So I'm going to take that balance, I'm going to subtract the allowed amount, and I'm going to reassign it to account, and I'm going to return the allowed value. It's the same exact algorithm as we used before. Same business logic, different approach. All right, similarly, the deposit, I'm going to add the amount to the balance, right? And there's no return. This is implicit none. Same API. and then I'm going to return the balance that way. Is everyone following this? Yeah. So we went from OO to no OO to functional. I'm calling it functional oriented, because if I said functional to this code, you'd be like, I don't think that's functional. But we'll see. All right, so let's look at context here. This is usage. So we create the account. So this is returning a dict, but we don't care what that is. It's black box. The API handles it. It's an abstraction. All right, we're going to withdraw it by passing that in. We have our amount withdrawn. We get the balance. It's our new balance, and we're going to print it. So it's exactly the same with just a little change here. But here's the context. So this question is, remember, in the case of clarity of intent, this context thing matters. And what we've done is we've removed this object-oriented class hierarchy problem, and we just have a function. So we do have to worry about balance. We do have to worry about where this, what is this thing, where does it come from, okay, and then it contains this balance. So we still have to know that, right? So we're interested in this thing, but there's no chance in this code here of implicit behavior because we've removed inheritance. We've removed multiple inheritance. There's no inheritance. This is the function, and this is how it's created. So there's still context, but it's much more simple. Here are the two functions. What happens if we run these two things in concurrent? What happens if we run these things at the same time? What happens? You have no idea. Yeah, that is one answer. Well, naively, you're like, oh, it just works. But in fact, you're in big trouble here because the count is being modified. This is the reference that's being modified here, and it's being modified here. So in this case, you have to worry about that. You need to think, how am I going to synchronize this? How am I going to make sure that this code, which is not thread safe, can be executed properly, safely? Right, so my bank doesn't go out of business. So it's still context that you have to worry about, that you have to know about. And would it be nice that, just like memory management, there's no memory management here. There's no new, there's no heap, there's no free, there's no free fund. We don't worry about memory management anymore. But this code, you have to worry about contention. Multiple thread access.
One other thing that you lost with the functions is polymorphism. So now if you want to have outdated account, you have to name those functions differently. And you can just treat the outdated account and regular account the same.
Yeah, so the observation here is by moving from OO to this, you lose polymorphism, which was really what was going on in the polymorphism there is saying I can apply the same functions to a single object and they behave differently. Now, I would argue that that's even, I haven't made that point, but that's even more context that you don't have to worry about. I haven't made that point just because I didn't, I just want to keep the sort of context, the point simple. But in fact, in OO, that is a big problem.
That's implicit function composition.
Yeah, well, I mean, it's dynamic. You're dynamically dispatching, and you don't necessarily know where things are going. So in OO, there's even more. So there's fewer things here still you don't have to worry about. But just on its face, by moving to the function-oriented, you've simplified and made explicit how that thing is initialized. So there's less context to worry about just by making that one decision. But you still have the concurrency problem. You still need to worry about how is this stuff going to behave when accessed concurrently. And in any language, you're going to have things like this. I mean, this is Python. This is very high level. If it's C, this goes up by a factor of 10 or more, probably more. Right? The things that you have to keep track of and know, the features of the language, and looking at any particular language, this context thing undermines the clarity of the author. How clearly is this code being communicated? So this is still a problem. So let's try to fix this by what I would call moving from a function-oriented to purely functional. So in a purely functional world, it looks like this. Same exact API, but there are two differences. And I'm going to highlight them. This function remains the same, and this function remains the same. The two functions that modified a count, we're going to change them. Because in a purely functional world, we don't want to modify things. We don't want what's called side effects. In the previous version, we had side effects. So we want to get rid of those things and make a copy, right? So let's take a look at this. So here's the withdraw function. And we've changed this. Rather than modifying a count, we never modify a count. But how do we change it? How do we change something if we can't modify it? Well, we don't. We create a copy of it with the correct state. So we do allowed, we create the new balance here, and then we return, rather than a modified account, we return two values. This is a tuple. This is the parentheses here. means it's a tuple. So 2 elements in a tuple. We return the amount allowed because we're still interested in that. But here's the cool thing. We return a new account. It isn't modified. Here's the old version. We're modifying a count in place. Boom. That's a side effect. So we keep calling this thing with the same amount. We're going to change. The result of this is going to be different every time. Another way of looking at a side effect is that it changes the universe outside of the function. So this is a side effect. And you have a side effect like this, you have a problem with concurrent access. If you don't modify anything, you've removed that problem. So rather than modifying the place here, we're creating a copy. Does that make sense? The output is going to be the correct state, but the original one wasn't modified. Similarly, the deposit, same idea. We create the new balance, and now we're creating a new account. That is the new account, but we never modify that account. That's the old version. So here we're modifying the account in place. So that's the side effect. So we're going to get rid of that thing. Here's how we use it. Instead of the previous one, which looked like this, where we just have a single value, we're actually going to have 2 values here as a result of that function call. But the rest looks very similar. Rather than getting the balance on the original, we're getting on the updated. So there's no change here. This is effectively immutable. This is the new account, and so we're going to get the new balance from the updated account, and then we print the result. That all makes sense? We're not modifying something, we're creating a count. That's it. All right, so here's the context. There's no OO, there's no inheritance, there's no polymorphism, there's nothing complicated there. Okay, good. Now what about concurrent access? Can we run, is this thread-safe code? Can we happily, pound, pour threads into this and run it and have the same results consistently every time? Yes? Yeah, it's true. Based on what we see here, that's true. But what I as a developer would worry about, this is context, is does all the code in my program behave this way? And that's a big question in Python. Python loves to modify state. Python will love to modify its own function when you call it, but if you're not careful. So it's very easy to change things in Python. So now I'm wondering, this feels safe. It's kind of complex, but I'm creating new things and it's kind of weird. But what I'm really worried about is the stuff that I don't know about. Because in Python, things can change. So it is true that this code naively looks like it's side effect free, and I can be safe, but I still, as a matter of context, need to worry about what other things could be going on here. That's why we have linters, or we have other, all sorts of things that we throw at our code, because we don't know in Python, in this particular case. So now I'm going to move to something which I call actually purely functional. It's not just a functional model, but it's actually, and to do that we have to move from Python to something else, because Python is not functional, or it's not purely functional. You can't use Python safely in this context to avoid these side effects. So I'm going to move to something which you can. This is like Erlang. Right? So I'm going to let you absorb this block of code. This is Erlang code. It looks sort of like Python, but not really. It has certainly the same shape, the same line count. Erlang is kind of like the Python of functional languages in my opinion. It's very simple, it's very direct. And it does, I think this code looks straightforward. So let's go through it. Same 4 functions, and you're going to see the same patterns. So we're moving from Python to Erlang. Don't worry, it's basically the same thing. We'll go through it. So the Python version, the creation of the new account was what? It's the creation of a dict. So it was some payload that had the balance. In Erlang, there is now, but let's get out. This is a convention in Erlang to create some sort of structure. And it's a tuple. So there are 2 elements in the tuple. The curly braces mean tuple. 2 elements, 1 and 2. This lowercase account is called an atom in Erlang. Basically, just represents itself. An atom is an atom. It can't be changed. It's not a variable. It can't be bound to some other value. It is the same as the number 1 or the number 2. It's just human readable in this particular case. In other languages, you might do red equals 1, or a constant, or a macro. So rather than passing 1 around, which represents red, you pass in a constant called red, green, blue. So you can read it, so you know what the intention is. So that's all an atom does in Erlang. And then here, the initial deposit is passed in. So I'm representing the payload of the account with that. Straightforward? Next. Withdrawal. The same account, that's the payload, gets passed in, and then the amount. Now in Erlang, this is kind of very cool. How many people here have worked with Erlang, know Erlang? Okay, no. It's like okay. So this is a really cool feature I want to highlight. It's called pattern matching. Erlang is sort of like it follows a logical or propositional calculus where things are true or false. So and these are expressions. So I'm going to call, well, this is a functional call. So I'm going to call this function with a couple arguments, and what will happen is Erlang will try to match the patterns, the shape or the pattern of this argument with this, the first argument with this, and the second argument with that. If the first argument is not a tuple, this will fail. You'll get an error. So this will not be called successfully. If it is a tuple of element 1, 3, 4, etc., it will fail because this is 2, and that will not match. It has to be a tuple of 2 elements. If the first element is not the atom count, it will fail. So you can't pass dog in, right? It won't work. You can't pass the number 1 in here. You have to pass a string in here. It has to be a count. And then finally, it will bind to this variable, this variable, the value of balance. So it's basically a way to assert that I expect this first argument to be an account. It's like type checking without type checking. It's very cool. I didn't define a type. I just made this little thing up. But I have effectively the same sort of type safety. It's just a runtime check. So it's going to do a pattern match when it's called, and it's going to succeed or it's going to fail. In this case, we hope it succeeds and we have a balance. And then amount will always be bound to the second argument. The rest of it's pretty straightforward. I'm going to calculate the minimum of amount and balance as we expect, calculate the new balance, and then return the allowed, and then the new structure. That's exactly the same as the Python. Same thing exactly. Similar with deposit, same idea here. Create the new balance, return the new account, and then this is even easier. I just return the balance, forget balance. Cool? Kind of? All right. Play around with Erlang, this becomes very second nature. You just sort of create these things and they pattern match, but like from an expression standpoint, it's exactly the same as the Python. Here's how you use it, new account, it's the same idea. I've got a tuple here, withdrawing my updated account, get balance, my new balance, and repeat the result. So what about context here? So this is the payoff for using Erlang. So that's my context. There's nothing outside of this I have to worry about. I'm even less worried about the new. Remember the other we were wording what's in that, what's like that dict? I'm less worried about it in the case of Erlang because it's kind of typed here. Like, I don't even care where this comes from. I just know that this is basically what I'm looking for. And somebody's telling me this is an account and here's the balance. I don't care. Like from just reasoning, I don't even care where this came from. I'm not worried about this implicit factory that had to create this thing and worry about it. I just know this is my API. Calculate the min, new balance, etc. So there's no context here that I can see. Can anyone see any other context outside of this function that you would ever have to worry about?
The virtual machine.
That's good. You have to worry about the virtual machine. You have to worry about the computer it's running on. You have to worry about the power supply. You have to worry about Earth. You have to worry about yourself. Yes, that's true. That's true. At that boundary. So we're gonna define a boundary there. But I would say, given that,
I think that there's more context to it. You say because there's the structure of account is something that you encode in all those the function signatures. And if you say you want to add a number to account, you will have to change all of those functions, even though it really doesn't affect them.
yeah, and I'm not sure that would be a change. I don't know if that would be a matter of context in for this particular function. So that's the context maybe for life. So the observation was that you do have to worry about this because you're sort of assuming that account is going to be that definition all the time. But what happens if you want to add more elements? Well, you have to add more elements this tuple. And so that's going to affect all the different functions that are associated with it. And that's true. But I don't think that for this particular expression, as somebody reading this code, and that's the point here, do I have to worry about anything else for this particular function? I think the answer is definitely you don't. Like, I don't care, like, you're bringing up sort of the future management of the system, but that's not this function. This function, to me, is context-free. I think so. I'm pretty sure it is. Okay. Deposit. So here we have the concurrent problem, right? Is this thread safe? It is. It's very thread safe. In Erlang, you can't modify state. There's no way to change state. So there's no contention for state in Erlang. That's why Erlang is known for its concurrent support of concurrency. You can have all these processes running, and as long as your functions are written this way, which is the side effect free, you can't change the variables. You have no choice in this particular case. It is safe. So I don't have to worry about concurrent access. I can look at this stuff and just reason about what's going on, free of context. So this is the point of functional programming. It is a propositional calculus. It moves from sort of the illogic of saying x can possibly equal x plus 1 to saying x definitively can never equal x plus 1. There's no value of x for which this will ever be true. The mathematicians here probably will say that's wrong. For me, this is always true. So it's always false. So we move from like this imperative model where we're saying, mutate this, change this, do this, hold all this thing, go over here, do this, we're sort of scattered all over the place to a mathematical expression, an expression which is true or false. And that's immutability. So just this step of going from things that can change to things that can't change, and a maintenance of logic, moving from poking things into memory, from asserting truth with things like this, right? Moving from assignments to logical statements, will remove a huge swath of things to worry about. And I want to give you an example. For me, that is beauty. Right? So for me, moving into a functional territory where you're cutting out a bunch of context, which could potentially confuse you and surprise things, and undermine the idea of what is this supposed to do? What does this person mean when he or she writes this code? Functional programming will greatly simplify that. So that's the beauty. So I want to show you an example of this. So I'm playing over here. I was reading this book, Programming on Purpose, which is a series of essays by P.J. Plowder, and this is back in the 1990s. And one of the chapters was on an algorithm, or contained an algorithm of the greatest common denominator. So this is a description of the algorithm. Greatest common denominator. You've got two integer values. What integer is the highest value that can be divided evenly into the two? And so if it's 6 and 2, then the answer is 2. If it's 6 and 3, the answer is 3, and so on. So the basic idea. So this is the algorithm. This is how you answer the question. What is the GCD of these two numbers? So the basic idea is to divide the small integer into the larger and keep the remainder. All right, that's simple. If the remainder is 0, the divisor, that is the thing on the bottom, is the GCD. Otherwise, you replace the dividend with the divisor, and the divisor with the remainder, then loop. It seems simple, but when I read that, I get confused. I'm like, I guess I understand that in theory, but I really, really don't understand this. So maybe if I look at the code, and he had a little pseudocode, maybe this will help me understand it. So here's the code. This is the pseudocode. So he had pseudocode, this is Python, it's exactly the same with the exception of like def and this colon. So, Python does a good job of representing pseudocode. All right, so that's the definition in English. Okay, got it. Confusion, let me read the code, maybe I can understand this. So then I started to read the code. M is the absolute value of M, N is the absolute value of N, well, N is okay, it's looping on this. There's temp, that's the division there. And at this point, right here, when I see temp, and that's the remainder, and then this is switching, and then I'm looping here. And I'm far less understanding of this than I did before. And I didn't have much understanding before. This is not helping my understanding at all. It's making it much worse. So I went back to the English. Okay. So divide and keep the remainder, got it. Okay. Remainder, okay, got it. And then I said, well, I'm gonna try to write this in Erlang, because I know Erlang is a functional language. It's going to help me. It's going to give me a better shot at reasoning about this code. It's going to strip away the context that's endemic to this. So here there's context. I've got this is state that's changing. This is state that's changing. This is a loop state that's maintained. There's context all over the place. This is basically a context-changing machine, right? And I have to reason about it, and my brain simply can't. I have to pray that this is right. I have to execute it. I have to test it, and then just hope that it's right. That's your basic Python C program. Right. So here's my attempt, my first pass in Erlang. Okay. So step 1, divide and keep the remainder. GCD is a function, 2 arguments. Okay, and I know I need to handle this somehow, but I don't know what's going on. I'm just basically trying to get the algorithm down as quickly as possible and pray that something cool happens. here's the integer division, that's going to create the remainder, and I know I have to handle this n because I know I return this if this is 0, so I know that much. If the remainder is 0, the divisor is the GCD. Okay, so this is going to do something, I don't know what it's going to do. If the result of this operation is 0, then return the divisor, which is n. So that's the thing on the bottom. Right. So this so far represents, I can start to reason about what's going on here. This represents so far what's going on. The next part is a little tricky. Else replace the dividend with the divisor and divisor with the remainder loop. Right. So that took me a while to figure out. Well, what's going on here? Here's the remainder. So this is a pattern match clause. And in Erlang, you can create multiple function clauses. So this is kind of like an if, it's like a conditional expression here. And when you call this function, it will say, does this pattern match? So if the first argument is 1, will it match? It will not match. 1 is not 0, so it will fail. Only when that first argument is 0 will this thing match, and you'll return whatever the second argument is. Does that make sense? The second version is whatever is not 0. So that's the remainder. So that's the I could probably call this non-zero remainder to be pedantic. But it's just the other remainder, and then I enter into this particular clause. Right? So I need to loop. When I hear the word loop in a functional language, I know that's a recursive call. So I'm going to call the function the same function. Sorry about that. That's what you call fat fingering the thing that you're holding. All right, let's get back to this. Okay. Yeah. All right, I'll try not to do that. My apologies. Okay. So I'm gonna do the loop. So I'm going to call, and I'm doing a replace here. So I'm flipping some stuff around. Okay, so I'm going to replace the dividend with the divisor. So that's the dividend here is what the top part. That's the remainder. Wait, that's n. So the divisor goes over here. That's the m part, and the divisor with the remainder. That's the remainder here. So this looks like m and n and loop. All right, I don't even know if this works or not, but I'm pretty sure it seems to be what is being said here. So I tested it and it worked. I ran the code, fine. Okay, so I know I have a working algorithm. Remember the premise of this whole thing is intent. When you call function do something, it's a pretty good sign that you don't know what you're doing and you're trying to communicate that to somebody. And the fact is, I don't know what this does. I don't even know what to call it. I just know it's a function. So I'm running this stuff. I often, if I don't know what's going on, I'll just call it do something, do this thing. But it's working. But I don't know what it is. So I need to fix this because I feel guilty. If you ship something called do something, you should probably feel some guilt. Right? I also spot here that there's a problem. If this is 0, this is going to blow up. So I can fix that by catching the 0 case up here and returning m. So that's what's going to go on here, is I'm going to catch that and I'm going to call this something else. Well, what do you call this? What is this operation? What is do something? So I looked at this thing, and the best I could come up with was this. Right, so here's the case of 0, so I avoid my divide by 0 error. Again, pattern match. If it's 0, it returns m. So in this case, I don't even know what this does. I know it's related to this algorithm, so I'm going to call it GCD underscore something. And I'm handling the remainder. It's slightly better than do something. It's slightly more descriptive. So I know it's going to work, I run it. But this is still not very clear. What the heck is this thing? I literally don't know what this is doing. So I'm like, well, this is what I was doing on the plane. I was thinking, this is like my thought process. I'm like, well, I don't know what this does, but maybe if I think about it, I reason about the arguments that's being worked on, look at these operations, I might be able to figure out what's going on. So you ever do puzzle pieces where you try, you think, okay, here's a piece that's going to map into this area, and you try it, and it doesn't fit. Sometimes you can just turn it, and you get lucky, and it fits. So what I'm going to do here is basically turn puzzle pieces. It doesn't fit. This is weird. I don't know what this is. I'm just going to like kind of mess around and see if my brain can kind of get a hold of this thing. So I'm looking at this thing going, okay, that's n. That's cool. I got that. This remainder. I wonder if this remainder is actually m, because this is n and m. Maybe this isn't a remainder after all. Maybe this is m. So what I'm going to do in this next step is just sort of turn the puzzle piece. I'm going to change this thing from remainder to m and see what happens to my brain. Right? This is like random flailing. This is like, I don't know, but I'm trying to understand what this is. So I'm just playing around here. All right, so now this is m and n. All right, so now my brain says, okay, this looks a lot like this up here, but the arguments are reversed. So what happens if I simply reverse the arguments. So I put the n over here and the 0 over here. Make it look like that. I don't know what I'm doing here. I'm just going to try it. We'll see what happens. So I flip it. So I have to flip this as well. That's the second function. So I have to make this consistent. I have to flip these two. That means I have to flip this one, and this one, and then this one, and this one. So if I'm flipping the arguments, I need to flip the call. Fair? I'm basically providing, I'm doing operations here that don't modify the functionality. So I'm testing this thing and making it work. But let's see what happens here. So that's the flip. So I went from this to this, flipped. Okay. So now it's starting to really look like this. So I'm kind of like having hope here. This is pretty cool. Then I think, what if this isn't n, but it's n? Maybe I got it wrong. I just guessed it. I called it n because the thing told me to call it n. But maybe it's actually m. I don't know. I'm just going to turn the thing and see what happens. So I'm going to replace this with m and m, and then flip this. So that's going to become m, that's going to become n, and change all of this. Everything else stays the same. And that's what it looks like. So then I looked at it. I'm like, wow, this not only looks the same, sort of, it is exactly the same. So I can just get rid of this thing and not have to call it anything at all. Right? I can just replace it with this. If you look at this thing, this GCD handle, I'm just going to call it to do something because I don't know what it does. It's exactly the same. M0, M, MN, right? Except rather than calling this other thing, I can just do this. That's really exciting. And then I thought, wow, if I, why settle for 3 lines when I can get 2 lines? So this is like, I'm like so happy because I went from this crazy sprawling thing to 2 lines of code. And that's just like a matter of counting lines. But then something truly magical happened in my brain. I looked at this thing and I didn't understand the algorithm up until this point. I saw the algorithm. Here's the algorithm. You can reason about it. It's like this. All this stuff up to this point was completely opaque to me. This is reasonable. This is saying this. The greatest common denominator of any 2 numbers, if one of those is 0, the other one is the answer. And I thought about that. I'm like, okay, it has to be, right? Because 0 can be divided by anything. And the greatest number, the highest, this doesn't accommodate a positive or negative. So you'll see this will return a negative if the negative is passed in. So that's perhaps something that you want to check. Let's assume this is positive. We can put checks on it. Any positive number is going to be the greatest common denominator when the other one is 0. That's just a fact. It's just a fact. So we're basically stating a fact here. But if it isn't, what are we doing here? This is effectively a search strategy, which is just flipping. So I'm going to perform a division here and get the remainder. And I'm going to try again, but I'm going to flip the order. So I'm going to basically flip back and forth, chipping down one side or the other side along the way using integer division. And there's something about integer division here which gets me to the greatest common denominator. But assuming that does the trick, I'm flipping back and forth until I converge on 0. So I start with a bunch of things and then flip, 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 boom, that's the result. So that's the strategy. And at that point, I'm like, I don't fully understand why this works, but really if you kind of sketch things out, you'll see, okay, I got it. This is the remainder. Anyway, you can dive into that, but assuming that will get you make some progress, and it does, this strategy is, I think, fairly clearly reflected here. If we go back to the way that we originally described this, divide and keep the remainder 0, and then we look further at this thing, to my brain, none of that is apparent. But when we look at this thing, it becomes apparent. So the clarity of intent is clear, right? The intent is clear. And that to me is quite clear. Right, so this is the brave new world of functions. So when we're refactoring and changing our approach from mutating state and managing all the complexity related to programming language, and we're moving to sort of a well-reasoned approach. What is going on here? What am I even saying? Does it work? Yes. That's not. We're not done yet. What does this mean? Functional programming languages let you do that more effectively than empirical. I believe that's just like incontrovertible fact. I'm trying to make the case here. Okay, so this is intent. What should this function do? And this is the centerpiece of functional language, functional programming. To answer the question, what should this function do? This is functional programming. So remember what it's like, do something? What does it do? What is this doing? What do I call this thing? Right? That process led me and forced me to further clarify. That's what I do as a functional programmer. It's literally every day. When I write programs, I'm thinking about what the heck I'm trying to do, what do I mean to do, what is this supposed to do, and trying to make it as clear as possible. It's a hard process. And this is something that's very common in my work. It isn't a matter of like theorizing and saying, oh, I'm a great philosopher, I'm going to, it's a matter of getting the computer to do what you want. But that isn't the final goal. The final goal is to be clear. To be clear to yourself, to be clear to your colleagues. And that's something I call, that's not something I call, it's something that is called rubber ducking. Who knows what rubber ducking is? Not everybody, that's great, so I have to explain it. I still want to explain it because I love it so much. So rubber ducking is when you put a little duck, it could be anything, something inanimate, but ducks are cute. So you put a duck out there, and you explain something to the duck. The duck can't question you, but when you're explaining something crazy to the duck, you somehow know that the duck knows that it's crazy. And you pause, and you say, I know you don't believe me, and then you have to go and figure it out. And that whole algorithm, the looping, the changing, I couldn't justify that to the duck. I couldn't get the duck to believe me because I didn't understand it myself. And the duck's like, sorry, nah, I don't get it. I'm stupid, I'm a duck. And then you go in and you pound on this thing. What's going on? What's going on? And then you explain the strategy, trying to find the greatest common denominator to the duck. And the duck's like, oh, okay, I get it. You get it. And you're happy because the duck is understood. So there's this process of sort of not settling. So the last point is to not settle. When you have this idea, right, which is programming, and you want to express it, it should be clear. If it's not clear, don't continue. There's more work to be done. Okay. So this is the context. Why am I going through all this stuff? I think, I don't like to say that it's a crisis in software because functional programming, this whole topic of sort of being deliberate and clear has been pretty well studied back in the 60s. It's like we're sort of rediscovering the principles of that people for almost half a century have been talking about. So I wouldn't say that there's a crisis, but really how many programs that you know actually sort of think about this and for whom clarity of intent is important. Functional programming languages give you a tool to express your intent more clearly. And that's why I think they really represent it's not just concurrency and multi-core and all these advantages, it's to help programmers really be deliberate and very, very communicative and very, very clear. So what's the payoff? Is it just because you're being clear, you want to express yourself clearly? Is that some arbitrary principle? I think the payoff is this. When you write code, and you walk away from that code, and you have to come back to that code. Remember the premise was that coding is an experiment. You try something, you see how it works, and you go back and change it. So maybe there's a bug in it, you got it wrong, maybe there's a feature change, you have to modify behavior. It's constantly changing. Even if there's code sitting there for years, it's always subject to the possibility of change. When you come back to that thing, and you come back to a well-reasoned, clear statement of intent, you can then reason about how it should be changed. It's a conversation. It's a conversation with yourself, a conversation with your colleagues. So you're writing this code for your colleagues and yourself. It's the same thing. It's social. Right? You have a responsibility, I have a responsibility for laying down clear, coherent, sensible, well-reasoned code. Because we're going to come back to it someday. If we have no idea what it does, we cannot effectively change it. And if you've ever debugged code that's insane and chaotic and completely incoherent, you understand this costs time. It often creates more bugs, so you're actually going in the reverse direction. Rather than fixing something, you're making it worse. Fair? You ever run into a case where you fixed a bug and you've created 2 other bugs? Right? It's because you have no idea what you're doing, because the person before you had no idea what he or she was doing. There was no clarity, you're just confused, and you're struggling, and you're thinking, that global variable set here, or that class hierarchy is over here, and you're trying and praying, and just maybe this will work. And it does, but then other things fail. It's a mess. This model of programming, which functional programming languages help you to comply with, it gives you a lot of tools to do this, will push that into history. So we can start to really be responsible and clear and thoughtful programmers. So to me, that is pure, unadulterated, angelic, pristine beauty. With that, this is question time. There's no reason. where are we at in time here? I think
Can
we're,
we do statements?
no?
Can we do statements?
Statements in Erlang?
No, statements instead of questions.
No. You have to put it in form that's like a Jeopardy. Put it in form of a question. Now, go ahead, make statements.
Why have you? No. I just wanted to mention that you sort of solved the object-oriented paradigm short here. Probably your purpose, your intent was to do that because you use multiple inheritance. When you do it, you're really asking for trouble. And like you can have a lot of object-orientedness without any inheritance at all, and it might be very useful.
So the observation was that I cheated and I poked, I exploited the great weakness of object-oriented programming by using inheritance and even using multiple inheritance, which even the most seasoned, aggressive, and reckless programmers can do these days. What is the point of object-oriented programming if not to provide
Abstraction.
subclassing, right? What's the point of it? I'm not talking about the sort of the esoteric definition, the frankly inaccurate definition. Some people say, well, it's message passing. It isn't message passing. Object-oriented programming today is Java. It's C++. You know, it doesn't matter what Alan Kay wrote in an email however long ago, what his intention and vision for Smalltalk. The reality is UML, object-oriented patterns and design, they are for Java. They are for C++. And those things are there for inheritance. So if you're in network C#, same thing. These things are designed around inheritance. So if you're saying, well, we don't use inheritance, then I would say you don't need OO. You don't need it. So don't use it. Go back to C. So I don't think it's unfair to poke at it because that's why that's the purpose of it. And people tend in practice to use it. And while you can use it differently, the fact is you don't need any of it. So these languages, you know, if you're stuck in OO land and Java, move to Clojure. If you're stuck in OO land and C#, move to F#. So find a language within your ecosystem that is politically viable, that isn't OO, and just maybe not use it. I'm not trying to you know, this isn't a religious discourse. This is like, I'm trying to be reasonable as sort of a data, as a social person and as a scientist and sort of thinking rationally about things. I'm not trying to be, you know, paint some sort of religion of functional programming. I would say this. If you're interested in, if you think that there might be some validity to this, if you buy any of this stuff, pick the functional language that is the next nearest to your comfort level, and that might take some research. It might be, if you're really into types and math, Haskell is your language. If you're sort of dirty and low level and pragmatic, Erlang. Erlang is a very pragmatic functional language. It doesn't get caught up with itself. As you can see, it's very, very direct. If you're in .NET land, use F#. You know, don't. So I was talking to somebody who wanted to use Haskell because it was so great and pure and pristine. That's true, but this person was in a .NET shop. F# is a great functional language within that context. OCaml, you know, there's all sorts of things. And if you really want to be dirty and you know, the Lisps are kind of functional. Clojure is a very, very good language if you're bound to the JVM. And there are constraints in Scala that could conceivably make it a functional language, and it's certainly called a functional language by some, but it's one to look at.
You kind of avoided the question, because, okay, so let's not call it OOP.
Yeah.
Let's say that some of us program with message passing paradigm. When you move to functional, I mean, unless you use something like type classes, you still have to somehow solve the problem that you have various kinds of things that sometimes behave a similar way. So either you're going to have something like type classes if you're in a pure language, or you're going to be rewriting a lot of code because you have some kind of logic that withdraws stuff from accounts, and you have 10 kinds of accounts that differ for some way, but not the way they handle the money.
So the observation is that there is in a domain certain behaviors that are independent of a underlying implementation. So you have sort of layers of abstraction, and you want to be able to capture a behavior of something and be able to throw different payloads at it, for lack of a better term. So you have some behavior that's at this level, and you have some behavior at that level, and you don't want to be copying and pasting code all over the place because that's a maintenance nightmare. There are patterns in functional language to handle that. So there are, so in Erlang, so it depends on the language. It definitely depends on the language. Erlang is a dynamically typed language. It doesn't have types. It doesn't have hierarchical types. Its types are low level, the primitives. They represent numbers and lists, and so it's a very straightforward language. And the payload can be sort of typified, and there are conventions in Erlang to do what you're describing. They're done all the time. It's basically a form of duck typing. So you have something that complies with an interface. So it provides a certain exported set of functionality. Those are actually called behaviors in Erlang. So Erlang can do that. And you can pass in a module name, or you can pass in a number of functions that can provide sort of the high level or low level behavior that you're looking for. So that's Erlang. In F#, you've got a really rich type system. In Haskell, you have a really rich type. In OCaml, you have a really rich type system. And you can do dispatch on the type. So you can have the same function, right, and you can throw in a different type, and it'll get handled by a different function. If you have generic behavior that you want, you can pass in a function to that function and have it delegate behavior. So there are different patterns of doing it. It's very convenient in OO. OO lets you do lots of things, so it's a little bit harder. But it slows you down a little bit, and it's all explicit. It keeps it in front of you in the function call. So you don't have to look upstream. It makes the context, right, it eliminates the context. So rather than having all of this implicit behavior that you have to sort out because of this sort of sprawling landscape of ontology, right, because you're modeling the world and this is, and all these other things, it's right there in front of you. Here's the callback. Call that if you want to know, if you want this thing to do something specific, and I don't know what it is, give me a callback and I'll call that. And then you can define the API for that and pass it in. So it's basically taking OO and inverting it. So it's all, rather than being all up here, it's all down here in front of you. And it's explicit.
Yeah,
I think that's better.
That's what is called very highly philosophically the expression problem. And every programming language worth its salt offers at least some solution to the expression problem. Maybe, well, none of them offer the perfect solution to it. All of them try to go as far as they can.
Yeah, the observation there is that this is called an expression problem. And one of the ways of looking at the imperative versus the functional code is the previous imperative code was comprised of statements that are executed. And the other one is a series of expressions which are more easily reasoned about in terms of meaning. So if you can somehow wrangle your code or your language, whatever environment you're using, to be more expressive in this sense of expressions, you can achieve that. I would argue, find a language, if you haven't played around with it, just try it to see what happens. You know, get a pet project that you have, so something on the side and see what happens. Nothing should ever be accepted because somebody else says it. You should try it and experience it. And you can learn alternative approaches that effectively achieve the same thing as OO, but do so in a different way. And then you can say, I like this better, I don't like this better. I ran into a situation where I had to get something done, and I was trying to do what I said, passing callbacks, and I just found that it was too much work, and I just used OO, and I was happy. So that's a confession. If this is a religion, I'm coming before you and I'm confessing this. I did that. So I think, it's pragmatically speaking, there's a lot of power in these abstractions, the OO model. So you can, in the same way that you can do a lot of good, you can do a lot of evil. I think it would probably be good.
We're lucky to have both worlds to choose from.
Yeah, I think so. We're lucky to have multiple worlds. And if that's your bag, Scala gives you multiple worlds. Anyway, any other questions? Observations, comments, rants, tomatoes? No?
I can really do because I think that in the code that you showed, the functional code, you completely skip the encapsulation that you could have detected. So if you have 4 functions, one that initializes the account, one that gets the balance, you didn't use the get balance once in the other methods, for example, and you could have just easily created a function that creates a new account based on a change in the account balance. That way, completely encapsulating the structure. And so if you had more of those functions that reach directly into account, knowing that it's either a dual tuple or hash, addict with key balance, that would become like pretty hard to maintain, right? Because those functions will be in different parts of the system. Once you decide that you want to change the structure, then you have to track them down. And if you have that small subset of operations that just manipulate the account, then it's just a very, very little subset.
So the observation is that this undermines this idea of encapsulation, where you want things to be a black box, and you want to sort of be able to define the black box in a way that is sustainable and truly black. And the approach of the functions here is that you have this payload that kind of leaks out into the world. So you're creating this account, and who knows what can be done to that along the way. And because you have functions, you can have them all over the place in different modules in different parts of the system. So how do you actually represent this thing in a cogent way? So there's two ways of looking at that. One would just be, you can do it through, if you have a type system, that will help a great deal to glue things together. Erlang doesn't give you that. It's a bit wild and woolly in that case. So then you might have to rely on convention. So by convention in Erlang, this would all go in one module. So you have a module that's devoted to the life cycle of this payload. And that's very common in Erlang. But I would kind of go further. I don't care. Like, so what? Like, two points. So what if you have functions in different parts of the system? As long as the functions are well defined and reasonable, you can understand what they do. Who cares what they do? Why do you have to have why are you trying to draw a boundary around all things that are related to this thing? Why not have a function over here that can do something else? I mean, why is that bad?
There's nothing that you have functions in different parts of the system that deal with accounts. That's what you usually need.
Yeah.
It's just the fact that they know the internal structure of the account.
Yeah. Okay. So, and that doesn't bother me as long as you know is what you're doing clear? Is it cogent? Is it actually practically maintainable and reasonable? I think the answer is in these cases you could certainly have another module which can handle that stuff. And then also, let's say you don't have any type checking and you've got sprawling code all over the place. As long as you can come back to the function and be reason about it, and things break, like you have a violation of something, or something failed, at least you can now reason about it without going through spaghetti code land, because your code is basically designed to create hundreds upon hundreds of side effects, and there's no way to reason about it. So even if you have the worst possible state that you're describing, I still think that's a superior state. Because if your code is reasonable, you can approach that code and fix the problem. Even the worst horrible thing that you're describing is better than most code that's
Besides, you
really
can
awesome.
write bad code in any language. You don't get to write bad code.
You're probably not persuaded by that, but it's a try. Okay, last one.
So I have pretty much the same observation about the encapsulation, so I'll just tell my observation about the topic. If we drop inheritance, local state, encapsulation.
Do it.
And
Drop it all. Kill it all.
Well, and if we drop it, but still use like object-oriented language for that, like Python, Scala, whatever, it will be much better code, easier to reason about. But then we'll be using the syntax that's we can just drop this syntax and just move on to another language. Yeah.
So yeah.
Well, that's.
So you're concerned that if you use these patterns in a non-functional language, you try to make a non-functional language look functional, you're going to lose sort of the
Expressiveness of the,
that,
the syntax.
yeah. It starts to look weird. I mean, returning tuples from Python is pretty weird. That's a weird thing. I would never expect to see that. If I saw that, I'd be like, what is this person trying to prove here? Like, why, so I would say there's a good reason to not use Python. So, I mean, I tend to use, use the idiom that the language wants you to use. But the fact is, there are functional languages that do a tremendous job. Erlang is one of them. There's not a lot you can't do with this language. All the system interfaces are very, very good. You just move over there and you can solve the same problems without the pitfall. But I would agree. I don't think you want to take C and try to do this. I don't think you're going to be. I just think you're going to have a heck of a time. But this is the payoff for functions. And you don't have to abandon these other languages for goodness sake. You don't abandon them. But if you don't have this as a part of your vocabulary, I think you're missing something. I think it's useful to do that. So I encourage you, if you're not, at least playing around with this stuff, to do it and experience it, and then you can form your own opinion. So with that, I'm all done. Thank you.